The usage of shape-changing structures has been widely discussed in the HCI field as a promising strategy for the physical representation of digital data. Such interfaces are expected to greatly impact a wide range of applications, like virtual reality, architectural design, and education of blind people, among many others. In a sense, many papers discuss the usage of pin-based shape displays where the shape-changing structure consists of a matrix of actuated pins, capable of dynamically rendering shapes. We believe that the creation of shape-shifting floors is among the most exciting applications for such structures. It will be particularly useful for virtual reality, but unfortunately, the implementation of much smaller shape-changing structures is already very expensive. The high cost of shape-changing displays is basically a result of the massive amount of actuators demanded when one actuator is used to actuate each pin. This expensive approach is currently the default strategy for building such structures. Despite that, the solution proposed by Peters shows that it is possible to reduce the amount of actuators to an amount that is proportional to the square root of the number of pins. With this approach, Peters became the 2014 Lemelson-MIT graduate winner. Such a reduction is expected to contribute to the construction of low-cost pin-based shape displays. But unfortunately, the solution proposed by Peters tends to make very slow displays, because pins are actuated one by one and not in parallel like they are in the default approach. As a result, time necessary to fully refresh the display also grows quadratically with display resolution, which potentially hinders the usage of the strategy with high-resolution displays. Given that, we present Bezalel, a solution for pin-based shape displays. In the worst case, the refreshing process using our solution requires a time that is proportional to the square root of the number of pins, and it can be as fast as the default solution in the best case. Additionally, our solution uses half as much actuators as the solution proposed by Peters. Our strategy relies on a novel multiplexing approach to achieve such an optimization. A typical approach to using shape displays is to use a rotary mechanism under each pin. Actuators are used to control the rotation of such rotary structures, promoting vertical translation of the visible part of the pin mechanism. Our strategy also converts rotation into vertical translation, but actuators are not directly used to determine the angle of the rotary structure. Instead, each actuator determines only the sine or the cosine of the angles under its influence. Each pin is influenced by a pair of actuators. Therefore, the pin height can be increased, decreased, or remain unchanged, depending on the resulting rotation of its rotary structure under the influence of both actuators. Given that multiple angles can have the same sine and that multiple angles can have the same cosine, our method allows each actuator to simultaneously influence multiple pins, regardless of their individual rotating action, which allows multiple pins to have their height updated in parallel. To exemplify our method, we render three images: a pyramid, a set of bars, and a rabbit. The pyramid and the bars are the best case examples for our approach. This means that our solution performs as well as the default approach for such images. On the other hand, the rabbit is an example of the worst case situation, where our strategy requires more steps to fully refresh the display. In this case, we are unable to actuate all the pins in parallel. The pins are, however, updated line by line. We believe the optimization techniques may allow arbitrary shapes to be rendered more efficiently using our mechanical model. The next step of our research is to explore such optimization algorithms and to create a physical implementation of the mechanical model. We hope that our solution will contribute to the creation of a wide range of low-cost actuated surfaces.